In this Mathematica Sessions video on discrete math, this is episode 5 of the series, we are going to look at mathematical induction, proofs by induction, and then elementary set theory. So you can see some of these problems here. If you're interested in that, then stay tuned. So here is our problems set. Can you see this, Jinya?
Yeah, I can see that.
Okay, great. So let's just begin by doing the first one here. And I'll make some space for it. Okay, so we've got a definition of a sequence. Okay, and so we're asked to show that an is equal to 5an minus 1 minus 6 an minus 2 for n greater or equal to 2. Sounds like someone else has come in. Okay, so I think I'll start just by listing some terms. Okay, so I'll get rid of this. And I'll come back to put some space here, because that's in a comment form. So I can just list some terms. Okay, because the definition is given here. So I'll just do that by writing some code. But it's really simple to see what I'm doing. So n goes from, let's see, 1 up to, say, 10. We'll just have a list of some terms. Okay, so this is the first 10 terms of this sequence. All right, which is interesting. But let's proceed now to do this. Okay, so we'll start with, because we want to show that the recursive definition holds, and we're given the closed form right here. So I want to take this part of the recursive definition, all right, and evaluate that using, sorry, I said recursive definition, but I mean to say recursive form that we're to prove yet. Okay, so I take the right-hand side of that, and this here, the closed form, is the actual definition. So we want to just simplify this. Okay, so copy and paste this one. Now I'm going to replace it with what we have in the definition, except what I need to do is, since that's a subscript n minus 1, I need to replace these n's with an n minus 1. All right, now the same for a subscript n minus 2, except the exponents will be n minus 2 for that one. Okay, great. So we've subbed that in. I've got to change these to n minus 2. But the next step is to ask, okay, how are we going to get this formula? Because if we've proved it, then we should get a subscript n in the end, right? Via the definition here. So we want to get this 2 to the power of n plus 5 times 3 to the power of n in the end out of this. So we ask, how do we do that? Well, we might want to collect like terms first, okay? So we'll take this line and we will expand the 5 over, distribute the 5 over. So let's do that. So that will be 5 times the 2 to the n minus 1. And then here we'll have 5 times 5 is 25. Okay, now we do the same with the 6 over here, and so this will be 6 times 2 to the n minus 2, and then we have minus 6 times 5. Okay, so now we've expanded each of those. So the next thing we want to do is collect like terms, right? But we can do some simplifying here. They're not. So the 2 to the power of n minus 1 and the 2 to the power of n minus 2, they're almost like terms, but not quite. So we want to make them like terms, okay? So that's the next thing we'll do here. And so we'll put them next to each other first. So I'll take this and I'll move it over here. Okay, and now we want to view these as like terms, but to do that, we need this to be a 2 to the power of n minus 1 rather than 2 to the power of n minus 2. So we can see here that 6 is 3 times 2, right? Which will allow us to put this 2 up here and have a 2 to the n minus 1. Now over here we could do the same thing, right? Because here we have 6 is 2 times 3. So we can write 2 and then we put the 3 right there. And then we can put the 2 and the 3 respectively up into the exponent. Okay, so that's our next step. So, right, so this part here, 2 times 2 to the n minus 2 is 2 to the n minus 1. And then over here we have 3 times 3 to the n minus 2, which is 3 to the n minus 1. Okay, great. So now we have like terms, right? 2 to the n minus 1, 2 to the n minus 1, 3 to the n minus 1, 3 to the n minus 1. So we can just add those. And so that will be our next step here. Okay, so let's see. We would take this out, factorize it out, and so we have this there, and then we can do the same with the 3's. So 25 minus 10. Okay, and we're nearly there because we just have to simplify what's in the brackets. So that is 2, and 25 minus 10 is 15, but we can write that as 5 times 3. And then you can see that we next get 2 to the power of n plus 5 to the power 5 times 3 to the power of n. Okay. All right, so we've just done some simplification of this. But now you see that this is the same as this, and so by definition, this is just equal to a subscript n. Okay, and so we've found that an is equal to 5an minus 1 minus 6an minus 2. And so we've proved what we were meant to there. Have you got questions, guys? Incidentally, welcome everyone. Let's see who we've got in the chat. We've got Jinyu, we've got Junyi, we've got Zi Xuan, and we've got Higao. Welcome everyone. I know I didn't pronounce your names correctly, but sorry about that. I'm glad you're here. Okay, so we'll go back to screen sharing and we'll look at the next question unless you have any questions of your own. I'll turn this into a comment now. I ordinarily leave it for as long as I can because it's a brighter color when I do that. And so if you joined in late, these are just the first terms of the sequence. So here's some code for doing that, which is pretty straightforward. All right. So let's have a look at the next one. So here we've got the Fibonacci sequence. So again, I think I will just write some terms of this for your sake. So I can use the same command to tabulate. Okay, and so I'm going to do this with the letter F, just so I don't accidentally put the A's in memory. So F1 equals 1, then F2 is equal to 1. All right, and I really want these outside the recursion. Okay, and then I'll just take this part of it and I'll be making a list of these. But as I said, I'm going to use F's for this little demonstration. Okay, and I'll want to tabulate this as n goes from, let's see, what do I want to put in first? I will put in a 3 first because when I put in a 3, I get 3 minus 2, and that's the first one here, right? F1. So we'll start with 3, and let's just do 20 of these. Okay, so this gives, I guess, the first 22 Fibonacci numbers if you include the 1 and the 1 that it starts with. Okay, good. So these are our Fibonacci numbers in case you didn't know what those are. Now let's go ahead and prove. So we want to prove the closed form, which is really nice, right? Because it allows you to generate each of the terms using just the n. So let's just do this as well, right? So I'll do some calculating here. So I'm just going to write replace all. Take the formula, and then I will replace n with a particular subscript value. Say, let's go for the 7th one and see what we get here when we do that. So see, you see a surd, right? But then when you expand this, so write that next, expand that, we get 13, right? Because you take the powers and the surds cancel, and you end up with a nice integer, and so that is the 7th Fibonacci number. Okay, great. So let's start to prove this now. So to do that, I want to introduce some letters, right? So first thing I'll do is we'll simplify this and say this is the same thing as if we take this 2, right? Because we have 2 to the power of n here, but we want to take this and make it a denominator in here. So I'm going to open up a little palette. I'm in Mathematica, incidentally, and so you have these buttons for this. Okay, so that would put a half there and a 1/2 on this one as well, but I now get rid of the 2 to the power of n in the denominator when I do that. All right, so that's what it's equal to, right? And so I now want to introduce some letters just to simplify the mathematics here. So let's call this, okay, so we still have this fraction over root 5. That I want to keep. But now we have the power of, and I'm going to call the first one 1 plus root 5 over 2. I'm going to call that phi. Where's my phi in here? Okay, this one. So that'll be phi to the power of n. And then we have minus. Okay, I'm going to copy and paste this, but I'm going to call this other one psi, or psi. I don't know how you say that, but it's this Greek letter here. Okay, so now I can close up that palette. So I want to call it this, right? So phi is equal to this first one, and psi is equal to the second one. All right, so I'll make this a comment because I want to do some calculating here for your sake as well. And so let's just take a numerical approximation of this 1 plus root 5 all over 2. Okay, and so what do you have? You have 1.61803 and so on, right? We can even take a few more decimal places here if you like. Okay, so this is a significant number in mathematics. It's a golden ratio, all right? So I'll do the other one as well. And so here we have minus 0.618 and so on and so on, okay? But both of these numbers are important in mathematics because they govern a lot of natural behavior. Like, for example, some people think that when markets go up and down, they like to come back down to a 61.8% level from the takeoff. You know? I don't know if any of you are into trading, but that's a relevant number when it comes to trading. Now, it could be a self-fulfilling prophecy because a lot of traders know about this, so they could be the ones that actually make that happen for all I know. Okay, anyway, so these are two important numbers, and so let's proceed to do this proof now. So let's see, I'll make this a bit more compact. I'll pull it up here so we can see. Now, what we want to do is we'll start with stating what we're trying to prove in a somewhat different way, all right? So what we want to prove is, well, not quite this, but we want to prove that an is equal to this, but I want to make it even simpler by multiplying by root 5 on both sides. Okay, so that I want to prove this identity for the Fibonacci numbers, because it's easier to deal with, basically. Okay, and I'm going to proceed by a strong induction argument. So what we do then is show that it holds for the first couple, right? And so in other words, there's a proposition, say P of n, right? And P of n holds true if this statement holds true. So first we want to say, okay, P of 1 and P of 2 hold, right? So we're meant to get the identity when we sub in 1 and when we sub in 2. So let's just do that. So A1, now that's when we put 1 into the exponent. Okay, but let's just verify this, right? So A1 is equal to 1. So that should be root 5 is equal to the difference between these values here, right? So this is this one minus this one. Okay, and so we put these under a common denominator and take the difference. So doing that, then we'll have 1 minus 1 there, and root 5 minus root 5, and that's just another plus root 5. Okay, which is 2 root 5, and then we cancel the 2's and get root 5. Excuse me. Need to drink some tea, but I'm running out. Right, also it holds for 1, and likewise you can show that it holds for 2, right? But I won't do the case for 2. All right, now let's make a strong induction hypothesis. So assume that P of k for all k less than n. Okay, so here's my strong induction hypothesis. And then by definition, so the definition is right here, right? Oh no, what I want to use is the induction hypothesis. So using the hypothesis, so following straight away from the hypothesis, which is that this holds for all k less than n. So change the n's to k. All right, except now I want to do so for k minus 1, right? Because under the assumption, then it holds true for k minus 1 also. And it holds true for k minus 2. So basically then our induction hypothesis means that we're assuming these two things. Where here I have a k minus 1 in the top and a k minus 2 in the second equation. Okay, so this is just our induction hypothesis. And so we'll say then, under the hypothesis, we have these two equations holding. Okay, so given that we have that, then we want to just add these together. So we'll just say adding these equations. So on the left-hand side, we have this plus this one. All right, and you can see that you can just factorize out the root 5. So let's just do that here. I'll get rid of that root 5 there. Okay, so that's the left-hand side of the sum factorized. Now on the right-hand side, we have this one plus this one here. Okay, but we want to add like terms eventually when we can. So we'll put the fees with the fees and the psi's with the psi's. Okay, and I'll just even factorize the minus 1 out of that as well. All right, any questions at this point? Okay, I guess not, so let's keep going. Now what we have common here, what we can factorize out of these is phi to the power of k, except we end up with negative exponents here. So let's just factorize the phi out of this. Okay, so I'll copy that. Actually, I want to copy this, don't I? And I'll factorize out phi to the k. So I want to pull phi to the k out, and then I will have no k's there, and I will have no k there. All right, and I want to do the same thing with the psi here. All right, but you can check that when you multiply this back out, you in fact do have phi to the power of k minus 1 and phi to the power of k minus 2. Okay, so we'll do the same thing here with the psi. Means getting rid of this k in the exponent. Okay, great. So we're getting closer to what we're hoping for, which is an expression that looks like this, but with k's. Now this would only work, I mean, it would only be what we're after if the things inside the bracket were actually equal to 1. Okay? Now, magically they are, but I'll show you exactly why at this point. Okay, so here I will claim. So I'll claim, first of all, that this is equal to phi to the power of k minus psi to the power of k, and then I'll say a because. Okay, so because these are actually both equal to 1, right? And for the moment, that might seem a little bit magical, but I'll show you exactly why. So both of these are equal to 1, since phi and psi are exactly the roots of the polynomial x squared minus x minus 1. Okay, and let's just verify that, because we've already taken the numerical approximations of both of those numbers, phi and psi. All right, so what I'll do next is I'll turn all of this into a comment, so I can do a calculation right here, just to show you that that's actually the case. Pull up some space. Okay, so what I want to do is solve an equation, right? I want to solve the equation x squared minus x minus 1 is equal to 0. So I'll just run that. And you see what the answers are right here. So we get x is equal to psi and x is equal to phi. Okay, so that claim is true, that phi and psi are the roots of this polynomial, right? So given that that's the case, how do we get that these add up to 1? So let's have a look. So simplifying this, what we have is basically phi to the power of minus 1 is 1 over phi. So 1 over phi, and then we have 1 over phi squared. So borrow this and then get rid of the minus sign there. All right, so what we want to do here is make those have common denominators, but when we do that, we have to multiply the first one by phi, right? So then we have in the numerator phi plus 1 all over phi squared. Okay, so I guess there wasn't a space there. Okay, so now we see the identity. So the identity, so this is equal to 1 since the identity here, replacing the x with a phi. So we have phi squared minus phi minus 1 is equal to 0. So phi squared is phi minus, or is phi plus 1. Right, so just copy and paste this one. Phi squared is phi plus 1, all right? And so dividing throughout by phi squared, you have 1. So that's why that holds. And because psi is also a root of this equation, the same identity holds true for psi, all right? And so now, and so this one is actually equal to what we had on the right hand side, which was using the definition And so I'll put in brackets here that this part, right, because this is just a note, is equal to, by the definition, because we've got the recursive definition for the Fibonacci numbers, so this is just equal to AK times root 5, right? So we've proved that AK times root 5 is equal to phi to the power of k minus c to the power of k, and that's what we're actually asked to prove, right? But we're not quite done. What we have to do next is state the principle of that it follows by this principle of strong mathematical induction. So the result follows by the principle of strong mathematical induction. Too many commas there. Okay, great. So that one's complete now. Do you have any questions? Stop the share and I'll have a look at. Okay, all good. You can just say so in the chat if you're too timid. All right, good. So go back to the share and we'll have a look at the next question. All right, so the next question, we've got another recursive sequence here, and we're asked to prove that for n greater than 1, t subscript n plus 1 is tn squared minus tn plus 1. Okay, I'll make some space for this. So this one's actually easier than it looks. So all we have to do, and we don't need induction for this, right? So we take our definition, all right? We start with our definition. Okay, we write, because before this we have a tn minus 1 as well, right? And so what we can simply do is put a bracket around this one there. And why don't we even pull the tn out in front? Okay, so this result holds by the definition. Right now, we can use the definition again and say what this is. Okay, so I'll just make a comment here. Since we have the definition that we can use again, right, except this time with taking 1 from the subscript, and so this would end with tn minus 1. We can then rearrange this algebraically and say that tn minus 1 is equal to this product here, right? So we'll say we have this product holding true. Okay, then that should be an equal sign here. All right, so that means that we can take what we have here in brackets and sub in tn minus 1 there. So let's just take that and work with this line. So this is equal to, and I'll take this and just sub in right there. Okay, and now all we have to do, because you can see that this is almost this, right? It's almost tn squared minus tn plus 1. All we have to do is expand. So let's do that expansion. So this is equal to 1 plus tn squared minus tn. And our proof is now complete, right? Because that's what we're asked to prove. All right, so I'll put a comma there and then it continues on because we have the word since. Okay, do you have any questions about that one? Seems like we're getting through these relatively quickly. Unfortunately, there's not a lot of back and forth between us. I guess because this is not a face-to-face session, right? So unfortunately, I'm doing a lot of the talking. Because I say that because it's a good thing for you guys to work on problems and for me to see what you're doing and have a chat about it, right? Okay, so let's move on and do the next one. 6.3, write the elements of these sets and state the cardinality, basically. So the first set, A, set of all integers such that x is equal to 1 plus minus 1 to the power of I, where I is an integer. Okay, so what we have when we enumerate the elements of this set, so when I is an odd number, we have minus 1, and 1 minus 1 is 0. But when I is an even number, we have plus 1. So we have either 0 or 2 in our set, right? So A is the set containing just 0 and 2. And then the cardinality of A, well, it just counts how many elements are in that set, and clearly there are only 2 elements there. Okay, good. Now let's have a look at the next one. The set of all y belonging to the integers such that y is greater than minus 8, but less than or equal to minus 5. Okay, so again, this is easy. B is equal to the set. Now, y is an integer greater than minus 8, so minus 7 is the next one. And then the maximum in this set is minus 5. So we go minus 7, minus 6, and minus 5. And there we have it. And now the cardinality of that set, there are 3 elements. So cardinality of B is equal to 3. And you can see that this is quite colorful, so let's make that a comment. Likewise up there. Okay, moving on, let's have a look at C. So the set of all integers s such that s squared plus 1 is 0. Now, this means that s is the square root of minus 1, right? Or plus or minus the square root of minus 1. But since those are not integers, this set contains no elements, and of course it is just the empty set. So we'll just say C is equal to the empty set. Down here, I believe I've got the symbol for the empty set already. So copy and paste that. Put it there. Okay, good. Now, how many elements are in the empty set? Well, if it's empty, then there are no elements in it. So the cardinality of C is equal to 0 because there are no elements in it. Okay, good. Now let's have a look at D. All right, so here we have the set of all integers t such that t to the power of 4 is equal to 1. Right, now this equation on its own has 4 solutions. They are the powers of the square root of minus 1. So we have plus or minus 1, and we have plus or minus I. But plus or minus I are not integers, they're just complex numbers. And so the elements of this set, because t is an integer, is just plus or minus 1. So D equals the set containing minus 1 and 1. And the cardinality of D is 2 since there are 2 elements. Great. Let's have a look at 6.4. Okay, so we've got 4 sets here, and so I'll give some space for these. 4 sets, V, X, Y, and Z. Now, let's just expand what these are, all right? So starting with V, because we're being asked to calculate unions and intersections and set differences and so on. So it will help to simplify this a little bit. So what we have in V, these are odd numbers, right? X is odd. And X is between 2 and 11 inclusive and an integer. So the odd integers in that range are 3, 5, 7, 9, and 11. All right, great. Now let's have a look at the next set, x. So x, these are integers between -1 and 4 inclusive. And so that's easy. -1, 0, 1, and 2, 3, and 4. Okay, good. And then we already have the elements of y written out, so we can move on to look at z. All right, now z is the set of integers that are non-zero. So we can write this in another way by putting z equals, well, the set z is equal to the integers without the set containing 0. Right, just to state that in another way. Okay, good. Now, I think we're ready to calculate each of these sets. So the intersection of x and v, right? So that's the common elements in both of these sets. So we see this one starts with 3, so the intersection there is 3. Hang on, have I got this right? Let me look at my notes. Yeah, it's just 3. Okay, so I've written those sets down correctly. All right, so the intersection of that, v and x, is just 3, a set containing 3. Okay, good. The union of v and y. So that's the elements of v and the elements of y together combined in one set. Of course, we don't have the duplicates. So I'll just copy and paste. Right, so we have a set with 3, 5, and 11 in it, but we also have some more. So that was v. Now we have the elements of y. Okay, these as well. So here, okay, but you can see we have some duplicates, so let's omit the duplicates. So 3 is duplicate. 7 is duplicate, and 9 is duplicate. So 2, 3, 5, 7, 9, 11. Okay, the intersection of x and z. Now, this is the question. Which elements are in x and also in z? So we have basically the entire set x except for one element, which is 0 is not in z, so we have to take that out. Okay, great. So this next one, x intersect the difference, set difference z minus y. So I'll just copy and paste the set x. And then I'll copy and paste the symbol. Okay, now let's simplify z minus y. So this is the elements of z that are not, well, when we take out y, okay? So basically, we can view this with a set difference. So in other words, the integers except for 0 and except for the elements of y. So we also do not have 2, 3, 7, and 9 in this second set. Now if we're taking the intersection, we're asking what are the elements of this set that are also in this set, okay? So here we do not have 2, 3, 7, and 9, or 0 in the second set. So simplifying that, we basically take those out of the set x. So we get rid of 0 because it's not in z. We get rid of 2 and 3, and we're left with -1, 1, and 4. Okay, great. So next one is x union y brackets and then intersect with a v. So let's calculate the union first of x and y. So union of x and y. So let's take the x, we'll put it there, and then we'll include the elements that are in y. Okay. So grab these and then I'll just put them here, and then I'll get rid of the duplicates. Okay, so 2 and 3 are both duplicate, And that's good. So that's the union, sorry, of x and y. But we still need to take the intersection with v. All right, but I can just grab v itself and place it there. And so now we can look at the intersection of these two sets. So what's in both of these two sets? Well, we can see that we have 7 and 9 common, and we have 3 common. And that's it. So just take these. And I'll get rid of the 4 there. So we have 3, 7, and 9. All right, good. Now let's look at the last one in 6.4. So x union y intersect v. Okay, so let's take x. And then the union of y intersect v. Okay, so y intersect v, which we haven't already calculated. So we'll just place this here and then calculate the intersection of these two. Okay, so what's common here? We've got 3, we have 7, and we have 9. All right, so intersect with 3, 7, and 9. Sorry, we're taking the union of these two now. Okay, so the union of these two sets, well, we just take the elements of this and we put it into the first one, for example. So I'll copy the first one and I'll include the elements of the second set, but we already have 3 in there, so all we need to do is include 7 and 9. Okay, and there's our union of those two sets, and that's the last question in 6.4. Okay, any questions? That was pretty straightforward. I hope you're able to write these at the same time as me. Now, the last question here is true or false, and it's rather easy, but it's a good idea to do anyway, even though it looks easy, because it clarifies a couple of issues for you. Hopefully, anyway. All right, so the first question is x an element of the set containing x? Yes, it's right there, so this one is true. Okay, now here I mean to say subset or equal to. So is the set containing x a subset or equal to the set containing x? So yes, true, because they're equal. So note that, true, because they're equal. Okay, next one is this, the set containing x, is it an element of the set containing x? Well, no, it is not. That's false. Right, because I don't see here within that set the set containing x. Right, x is in fact an element of this, but the set containing x is not an element of the set containing x. All right, so next one is the set containing the empty set an element of the set containing the empty set? Yes, right? So true. Put y equal to the set containing the empty set, and then the question is y an element of? Is y an element of the set containing y? There's yes. All right, good. Okay, second last one. Is the empty set a subset or equal to the set containing x? Yes, it is. So true. In fact, the empty set is a subset or equal to every set. Okay, finally, is the empty set an element of the set containing x? No, it's not an element because it's not present there. So this one is false.